somewhere in the darkness between the stars, and stretching far beyond the visible edges of every galaxy, lies the great unseen bulk of the universe. Dark matter is the dominant form of matter in the cosmos, outweighing all the ordinary matter of stars and planets and gas by roughly 5-1, and yet it has never once been directly observed, betraying its presence only through the pull of its gravity. It emits no light, absorbs none, and scatters none. It is dark not in color but in its utter refusal to interact with light at any level we can detect. And its existence is not the guess of a single measurement, but the convergence of many independent lines of evidence, from the whirling of galaxies to the faint structure of the oldest light. Together they point to the same startling conclusion, that about a quarter of everything is made of some cold, invisible substance that is not the ordinary matter of which we and the stars are built. This chapter follows the evidence, the suspects, and the search. The story of the missing mass begins, as so many do, with an anomaly that was ignored. In 1933, the Swiss astronomer Fritz Zwicky, studying the Great Coma cluster of galaxies, applied a simple and powerful law of mechanics that relates how fast the members of a bound system move to how much mass holds them together. The galaxies of Coma, he found, were hurtling about far too fast to be held by the gravity of all their visible stars, so fast that the cluster should long since have flown apart. To keep it bound demanded vastly more mass than met the eye, and Zwicky gave that unseen mass a name that has stuck ever since: Dunkelmaterie, dark matter. For decades the community largely set his result aside, for cluster dynamics were poorly understood, and the discrepancy could always be blamed on some error of measurement. The missing mass would have to be rediscovered before it was believed. The rediscovery came in the 1970s, and it came from the patient study of how galaxies spin. Working with a sensitive new spectrograph, the American astronomer Vera Rubin and her colleague Kent Ford set out to measure the rotation of spiral galaxies, beginning with our neighbor Andromeda and building to a landmark survey of 21 spirals. What they found overturned expectation. In the solar system, the outer planets orbit more slowly than the inner ones, because nearly all the mass is concentrated in the Sun at the center, and the stars in the outskirts of a galaxy, where the light thins to nothing, ought to orbit more slowly for the same reason. Instead, the orbital speed stayed stubbornly flat, out to the very limits Rubin could measure and far beyond the glowing disk. The stars at the edge were moving as fast as those within. It was as if each galaxy were embedded in a vast, invisible cocoon of mass, a dark halo, dwarfing the luminous galaxy at its heart. The physics of that flat rotation curve is simple and damning. The speed at which a star circles depends on how much mass lies within its orbit. Beyond the visible disk, where no more stars are added, the speed should fall away. That it does not means the mass must keep on mounting, steadily and invisibly, with every step outward into apparent emptiness, the dark halo containing several times the mass of all the galaxy's stars combined. It is worth being scrupulous here about what is proven and what is merely inferred, that there is a gravitational discrepancy, that the visible matter alone cannot account for the motions we see, is among the most robust facts in all of astrophysics. But whether the cure is a new kind of matter, or instead a flaw in our law of gravity itself, is a separate question entirely, and one this chapter will keep firmly in view as the evidence accumulates. At the scale of galaxy clusters, Zwicky's original argument has only grown stronger, and it is now cross-checked 3 independent ways. The velocities of the member galaxies, weighed by his law of mechanics, give one estimate of the total mass. The temperature of the searingly hot gas that fills the space between the galaxies, glowing in X-rays, and held in place only by the depth of the gravitational well, gives a second, through entirely different physics. And the bending of light from more distant galaxies behind the cluster gives a third. All 3 agree, and all 3 find the same thing, that the luminous matter, the stars themselves, account for only a few % of a cluster's mass. In a typical great cluster, something like 80 or 90% of the mass is dark, a further tenth or so is the hot X-ray gas, and the stars, everything we can actually see, are a mere garnish on the whole. The most precise evidence of all, however, comes not from any single galaxy or cluster but from the infant universe, where the physics is clean and beautifully understood. Imprinted on the microwave background, the relic radiation of the hot early cosmos is a series of harmonic peaks, the frozen echoes of sound waves that rippled through the primordial plasma. The pattern of those peaks is exquisitely sensitive to what the universe was made of. Ordinary matter, the baryons, adds weight to the oscillating plasma and deepens every second peak. Dark matter, feeling no pressure and simply deepening the gravitational wells, leaves a different fingerprint. And the decisive clue is the third peak. In a universe of ordinary matter alone, each successive peak would fall lower than the last, but the observed third peak is boosted, lifted up, and that boost is direct evidence of a non-baryonic, gravitating substance that was already present when the universe was less than 400,000 years old. Measured to extraordinary precision by the Planck satellite, this pattern fixes the cosmic recipe. Dark energy makes up about 69% of the universe, dark matter about 27%, and ordinary atomic matter, everything the periodic table describes, a mere 5%. Dark matter outweighs the ordinary kind by more than 5 to 1. And a wholly independent check confirms that it cannot be ordinary matter in disguise. The abundances of the lightest elements, forged in the first minutes of the universe, depend delicately on the density of baryons, and they pin that density to a value that agrees precisely with the microwave background, and which is far too small to be the whole of the matter. Whatever the dark matter is, it is not protons and neutrons hiding in some faint or frozen form, it is something else, something new. The one nagging caveat concerns the expansion rate, where local and cosmic measurements disagree, the so-called Hubble tension, but that is a puzzle about dark energy, not about whether dark matter exists. There is a way to weigh the universe that assumes nothing at all about motion or equilibrium, and it offers the single most persuasive demonstration that dark matter is truly matter. In Einstein's theory, mass bends the very fabric of space, and so a massive, foreground object distorts and magnifies the light of galaxies behind it, gravitational lensing. Because this bending responds to all mass, seen or unseen, it maps the total gravitating substance directly, and everywhere it finds far more than the light can account for. The masterpiece of the technique is the bullet cluster, two clusters of galaxies caught in the act of colliding. As they passed through each other, their hot gas, the bulk of their ordinary matter, collided, shocked and slowed, lagging behind in the middle. But the galaxies and whatever dark matter accompanied them, being effectively collisionless, sailed straight through and out the far side. The lensing reveals where the mass lies, and it lies not with the gas, but out ahead with the galaxies, cleanly separated from the ordinary matter. That separation is the crux. The center of gravity has come apart from the center of the visible baryons, and this is extraordinarily hard to explain by tinkering with the law of gravity while keeping mass tied to ordinary matter, for in any such theory the lensing should peak where the gas is, and it does not. A survey of dozens of such colliding clusters established the offset collisionless mass at overwhelming confidence and set limits besides on how strongly the dark matter can interact with itself. The bullet cluster does not, by itself, tell us what the dark particle is, but it shows about as decisively as astronomy can that the gravitating mass is a distinct substance, decoupled from the ordinary matter, exactly what a cloud of collisionless particles would do, and exactly what modified gravity without dark matter struggles to accommodate. Before reaching for exotic new particles, good sense demands we rule out the mundane. Might the dark matter simply be ordinary matter in some hard-to-see form? The leading such candidates were nicknamed macho, massive compact halo objects, faint bodies like burnt-out white dwarfs, brown dwarfs too, small to shine or stray black holes, drifting unseen through the galactic halo. Such objects would betray themselves by microlensing. Should one drift across the line of sight to a distant star, its gravity would briefly focus and brighten the starlight in a characteristic way. Two great surveys watched millions of stars for years, and the verdict was decisive. There are nowhere near enough such objects to make up the halo. Combined with the hard limit from the early universe, that there are simply too few baryons in total, the door on an ordinary matter solution is firmly closed. Even the ghostly neutrino fails, for it is too fast and too light. Moving near light speed in the early universe, it would have smeared out the seeds of structure, giving a cosmos quite unlike our own. The dark matter must be cold, and it must be new. The particle that dominated the hunt for 3 decades was the WIMP, the weakly interacting massive particle, a hypothetical body some tens to hundreds of times heavier than a proton, feeling only gravity and the feeble weak force. Its appeal rested on a beautiful coincidence known as the WIMP miracle. In the hot early universe, such particles would have been continually created and destroyed in balance until the expanding cosmos thinned them out and their mutual annihilation could no longer keep pace, at which point their number simply froze, leaving a fixed, relic abundance ever after. That leftover abundance depends only on how readily the particles annihilate. And when one works out the value needed to leave exactly the dark matter density we observe, it turns out to be precisely the annihilation strength of a particle of around 100 proton masses interacting through the weak force, a particle proposed for entirely separate reasons in the physics of the very small, such as the lightest stable partner particle predicted by supersymmetry, would naturally supply just the right amount of cosmic dark matter with no fine-tuning at all. That two utterly separate domains, particle physics and cosmology, should point to the very same particle was electrifying, and the WIMP became the focus of a vast experimental effort, precisely because it was testable in three complementary ways. One could try to catch a dark particle from the halo as it struck an ordinary nucleus in the laboratory. One could look to the heavens for the telltale radiation of dark particles annihilating in dense regions of space. Or one could try to manufacture them outright in the collisions of a particle accelerator. Yet it must be said plainly, despite 30 years of ever more sensitive searching, no WIMP has ever been found. The simplest, most favored versions of the idea have been steadily squeezed and excluded by the mounting silence. This has not killed the WIMP, large viable regions remain, and the freeze-out logic is sound, but it has broadened the search and turned the WIMP miracle itself into an open question, a genuine clue or a tantalizing coincidence. The most compelling alternative is the action, a particle so light and so weakly coupled that it is almost a ghost, and which arrives bearing an unexpected gift. It was first proposed not to explain dark matter at all, but to solve a nagging puzzle in the theory of the strong nuclear force, why that force, which in principle could, appears not to violate a certain deep symmetry of nature. A new symmetry, proposed in the 1970s, would resolve the puzzle automatically, and it implied the existence of a new, extraordinarily light particle, the action. And here was the gift: if such actions were created in the early universe as a great coherent field, settling slowly toward rest, they would behave exactly as cold dark matter, despite each one being fantastically light. To catch them, experiments exploit the action's faint tendency in a strong magnetic field to convert into a single microwave photon. A finely tuned resonant chamber can amplify that whisper of a signal, but because the action's mass is unknown, the search must proceed as a slow scan across frequencies, listening patiently, band by band, a wholly different discipline from the WIMP hunt. Beyond these two frontrunners lies a whole menagerie of possibilities, and as the classic WIMP window has narrowed, the field has deliberately cast its net wider. There are sterile neutrinos, heavier, shyer cousins of the ordinary neutrino, which might slowly decay and emit a faint X-ray line. Indeed, a disputed signal at one particular energy has been argued over for years without resolution. There are hidden sector particles that touch our world only through the narrowest of portals. There are particles so feebly interacting they were never in equilibrium at all, but slowly trickled into existence. There is fuzzy dark matter, so absurdly light that a single quantum ripples across a whole galaxy, its wave, nature perhaps smoothing the centers of halos. And there are primordial black holes, forged in the first instance and viable within narrow windows of mass. The candidates span some 90 orders of magnitude in mass, from the fuzzy to the black hole, and the range itself confesses an uncomfortable truth. Gravity tells us with precision how much dark matter there is, and almost nothing about what it is. The campaign to catch it directly is a triumph of patience and shielding. Deep underground, sheltered from the rain of cosmic rays, sit great tanks of liquid xenon, chilled and still, waiting for the exceedingly rare jolt of a dark particle striking a single xenon nucleus, a recoil of only a few tens of thousands of an electron volt, a whisper of energy that must be caught against a hush of near-perfect quiet. The leading experiments now weigh several tons and have watched, for years. The most sensitive, reporting in 2024, saw nothing, and in seeing nothing set the tightest limits yet on how weakly a WIMP may interact. These detectors are now so exquisitely sensitive that they are beginning to register neutrinos from the Sun, an irreducible neutrino fog that will, in time, set the ultimate floor on this kind of search. One long-standing claim of an annual signal has never been reproduced by any other experiment and sits uneasily against the global silence. The other two fronts have fared no better. The indirect search scours the sky for the debris of dark particles annihilating, gamma rays streaming from the dark matter-drenched dwarf galaxies that orbit our own, or from the crowded galactic center, and antimatter drifting in the cosmic rays. There are tantalizing excesses, a glow of gamma rays from the galactic center, a surplus of cosmic ray positrons, but each can be explained by more mundane sources, spinning pulsars and the like, and none has been confirmed as dark matter. And at the great particle accelerators, physicists have tried to conjure dark particles from raw energy, watching for collisions in which momentum simply vanishes, carried off invisibly. They have set strong limits but found no signal. The collective null result is one of the most important facts in the whole field. It has not excluded dark matter. The gravitational evidence is overwhelming and untouched, but it has swept away the simplest expectations and driven the search toward broader ideas and ever quieter detectors. For all the mystery of its identity, dark matter's grandest role is beautifully clear. It is the scaffolding upon which the entire visible universe was built. In the hot early cosmos, ordinary matter was shackled to the radiation, and the fierce pressure of light prevented it from clumping. It could only oscillate, ringing like a bell. But dark matter, deaf to light, felt no such restraint, and its gravity began quietly drawing it together into clumps long before the ordinary matter was freed. By the time the baryons at last slipped loose, the dark matter had already dug deep gravitational wells across the cosmos, and the ordinary matter came tumbling in, its structure building enormously accelerated by the ready-made scaffolding. Without that head start, the faint ripples we see in the microwave background, mere parts in 100,000, could never have grown in the time available into the galaxies and clusters that fill the sky. The very existence of structure, on the schedule we observe, is itself a fourth great pillar of the evidence. The universe as we know it could not have assembled without the unseen mass. This picture, cold dark matter plus the dark energy driving the expansion, is the standard model of cosmology, and on the largest scales it is a triumph. Cold means the particles moved slowly when structure began, so that the smallest lumps survived and grew. The result is a bottom-up history, in which small halos form first and merge into ever larger ones. Vast computer simulations, evolving billions of particles under nothing but gravity, reproduce the observed cosmic web, its filaments, its clusters, its yawning voids with uncanny fidelity, and they predict a near-universal shape for the density of every dark halo. Yet on the smallest scales the picture frays, and honesty requires naming the tensions. The simulations seem to predict more small satellite galaxies than we actually see, and denser, more sharply peaked halo centers than some dwarf galaxies appear to have. Whether these are real failures of the cold, collisionless assumption, hinting at a warmer or self-interacting or fuzzy dark matter, or merely the complicated, hard-to-model effects of exploding stars and gas within small galaxies, is genuinely unresolved. The grand design is secure, the fine print remains a frontier. Because the whole edifice rests on gravity alone, a skeptic is entitled to ask whether the fault lies not in some missing matter, but in our law of gravity itself. The leading such proposal, modified Newtonian dynamics, suggests that below a certain tiny threshold of acceleration, the regime found in the outskirts of galaxies, gravity, departs from Newton's familiar law. This single, elegant adjustment reproduces the flat rotation curves of galaxies remarkably well, and it explains, seemingly for free, a tight and long-observed relationship between a galaxy's ordinary mass and the fourth power of its rotation speed, a regularity that the dark matter picture must work harder to account for. On the scale of individual galaxies, this modified gravity is genuinely, impressively successful, and that success is a real fact that any complete theory must one day absorb or explain. And yet most cosmologists regard modified gravity as unable to replace dark matter for three stubborn reasons. It fails on the scale of clusters, which still demand extra unseen mass even after the modification. It struggles profoundly with the bullet cluster, for by tying gravity to the ordinary matter it predicts the lensing should follow the gas, precisely where the lensing is not. And a theory of modified gravity, to describe the microwave background and the expanding universe at all, must be made compatible with relativity, and the versions built to do so have strained to reproduce that telltale boosted third peak that the dark matter model fits with a single number, while the observation that gravitational waves travel at exactly the speed of light, confirmed by a neutron-star merger, quietly ruled out a swat of them. The mainstream verdict then is that dark matter as a particle is strongly favored, the one hypothesis that accounts quantitatively and all at once for the rotation curves, the clusters, the lensing, the microwave peaks, the light elements and the growth of structure. And so we arrive at one of the deepest and most honest open problems in all of science. That there is more gravitating mass than there is light is beyond serious doubt. established by half a dozen independent lines of evidence that no single error could conspire to fake. But what that mass is remains entirely unknown. The particle has not been caught in any laboratory or any telescope, the small-scale puzzles linger, and the galaxy-scale successes of modified gravity remain a genuine, unexplained clue that keeps the skeptics honest. Dark matter is a phenomenon we can weigh to a fraction of a percent and yet cannot name. Its resolution, whether by the long-awaited flash of a particle in an underground tank or by some deeper revolution in our understanding of gravity itself, would rank among the great discoveries in the history of physics and would reshape our picture of the universe from the largest structures down to the very nature of matter. For now, the darkness keeps it secret.